In this video, we're going to talk through an example problem where we can figure out how heavy you are or what the gravitational force of attraction would be on you if you were on not just the Earth, but some planet where we know the density of that planet and the radius of curvature of that planet. If you're standing on its surface, because you have mass and because that planet has mass, there's going to be a gravitational force of attraction that's the same size between you and the planet. And the question is, how big is that gravitational force of attraction? So we're also going to solve this symbolically before we start plugging numbers in. So the problem statement reads, what is the gravitational force of attraction between a 100-kilogram person standing on the surface of a new planet? Assume the planet has the same density of the Earth, but has a radius that's 1/2 the Earth's radius. So like I said before, we're going to solve this symbolically to talk about how could we think through this problem with proportional reasoning before we start plugging numbers in, like the actual radius of the Earth or the mass of the Earth or the density of the Earth. So we know that the size of the gravitational attraction between two masses is given by Newton's law of universal gravitation. The universal gravitation constant times the mass of the first object times the mass of the second object in kilograms divided by the separation that the center of those masses are separated, squared, right? And so in this context, we've got the mass of a planet and the mass of a person. So let's just do this symbolically. So we've got big G, our universal gravitation constant, times the mass of the planet multiplied by the mass of the person divided by the radius of the planet squared. And why are we using the radius? Well, remember that R represents how far away the center of both masses are from one another. The center of the planet is right here. The center mass of the person is here, but this is certainly not to scale. So the R that we'd plug in would be, essentially from the center of the person to the center of the planet. But the added distance from the person's feet to essentially their belly button is an insignificant distance compared to the full radius of the planet. And so we're just going to kind of simplify that and say that's just the radius of the planet right there. Well, this is a symbolic expression that gives us that, but in this case, we don't know the mass of the planet, or we're not given a variable to describe it. We're just given the density of the planet and the radius of the planet. And so we need to come up with an expression or substitute for this m something that has density and r in it. Well, how is the mass of the planet related to the density of the planet? It kind of goes back to the definition of density. So density of anything or of a planet is equal to the mass of that thing divided by its volume. Remember, density has units of kilograms per cubic meter, mass in kilograms divided by our volume units in cubic meters. If we rearrange this equation to solve for m, we multiply each side times the volume, we get that the mass of the planet, or the mass of anything, is just equal to the density of it times its volume. Density, remember, is in units of kilograms per cubic meter. Volume is in units of cubic meters, and so cubic meters would cancel and we'd be left over with mass. And so before we plug some stuff in here, density, that's a variable that's given, but we're not given the volume of the planet. Well, what's an expression for the volume of a sphere? All right, this planet is spherical. All planets are spherical. So we need to substitute in place of V the equation for the volume of a sphere, which is just 4/3 pi r cubed. So the mass of the planet is equal to its density times 4/3 pi r cubed, r being the radius of the planet. So this right here is an expression that's equivalent to the mass of the planet. And we're given the density, we're given the radius. Those are acceptable variables to have in our equation for our symbolic solution. And so let's just take this and plug that back in for the mass of the planet in our universal gravitation equation. So it looks like this. The size of the gravitational attraction between the planet and the person, which would be the person's weight standing on the surface of the planet, would be equal to the universal gravitation constant, big G, times the expression we found for the mass. The density of the planet times 4/3 times pi times the radius of the planet cubed. That's all times the mass of the person up here. And we have to divide that whole expression on top by the square of the planet's radius right here. Okay, before we go any further, notice there's some radius terms in the top and the bottom. So we've got r cubed up top, we've got r squared down below, so we can cancel the r squared below, and we're left over with just one radius in the numerator there. So our final symbolic expression, which tells us the gravitational force of attraction between the planet and the person, which is equal to the person's weight, is just 4/3 times the gravitation constant times the density of the planet times pi times the radius of the planet times the mass of the person. So this symbolic expression is true regardless of the size of the planet or the radius, the density of the planet, or the mass of the person, right? So we could actually go back and answer this question up here, what's going to be true of the gravitational force of attraction if the density stays the same as that of the Earth, but the radius is 1/2 the size. So when we look at this, if density stays constant, g is constant, 4/3 is constant, pi is constant, and if we're talking about the mass of a person, right, whether they're on the Earth or this new planet, their mass is constant. So we can see that the weight of somebody, looking at our expression, is proportional to the radius of the planet. If everything else is the same between the Earth and this planet, if this new planet has half the radius, proportionally, that means their weight should be exactly 1/2 of what we would expect it to be on the Earth. Well, if we had a 100-kilogram person standing on the Earth, gravitational field strength of the Earth more precisely is 9.8 newtons per kilogram, we would expect that the gravitational force, or their weight on them, would be 980 newtons. So we would expect the weight on the new planet to be about 490 newtons. That's half of 980. Well, if we go ahead and take the values, if they're given, and plug them into this equation where the density of the Earth, same as the planet, is 5,510 kilograms per cubic meter, we take the radius of the planet, which would be half of the value for the Earth, and we plug that into the radius. And we take the 100 kilograms and plug it in there, and we multiply all that stuff out. We end up getting what we expected or predicted with our kind of proportional reasoning is it's about 490 newtons. Using specific values, it turns out to be precisely 491.1 newtons.